We've learned about the first law of thermodynamics, and we've learned that the energy can transfer between the system and the surrounding by heat and work. Okay, so now we've had some example in the previous video that we were defining the change in the internal energy. You've been given the amount of heat and the work, but it's not always the case to be given that this is the Q, this is the heat. So you have to find the Q. They give you some information, therefore you can find the Q. So in this video, we're going to talk about that. So to quantify the heat, and it's not heat and work, so it's just heat. So I forgot to delete that. So in order to quantify the heat, so first we have to know what is the heat. We talked about that in the previous video, so to know that heat is transfer of thermal energy, right? You have to know that the heat, the thermal energy always going from the object with the high thermal energy that has, like the molecule have more movements, to the object with a lower thermal energy, okay? So temperature is a direct measure of thermal energy. So the item with a higher temperature has higher thermal energy, and the item with a lower temperature has lower thermal energy. Okay, so how do we measure the heat? So the term you have to learn is the specific heat capacity. The specific heat capacity is the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. So if you remember when we were talking about, I think it was a units of energy, about calorie, so it says 1 gram of water for 1 degrees, and I said it matters if you say water, because if you have different items, different matters, we have different amount of energy, okay? So, and that is the specific heat capacity of that element, okay? So the specific heat capacity is the amount of energy required to raise the temperature of 1 gram of that substance by 1 degree Celsius. Okay, so that's the energy. So that if you see the unit, it's in joule per gram per degree Celsius, right? The amount of energy in joule over a gram of the compound for 1 degree Celsius. So that's the unit, but sometimes you might see different units. So any unit that says the energy, the heat is kind of energy, right? So the unit is joule or kilojoule. It might be kilojoule per gram per degree Celsius. So that's the amount of energy in kilojoule, or it might be, excuse me, not kilojoule. It might be joule over gram per degrees Kelvin. It doesn't matter. It's the change is a change of temperature in Kelvin, which is the same. 1 degrees Kelvin is the same as 1 degree Celsius. So you might see these units, but the most common one is joule per gram per degree Celsius. So if you think about it, if you have 1 gram of water, for example, or anything, and we want to increase the temperature by 1 degree Celsius, that the heat that is required for that is a specific heat capacity, and that's specific for each element, okay? The heat capacity that is showed with a uppercase C, for example, if you have, instead of 1 gram, if you have 2 gram of that element, for sure it needs more amount of energy, more amount of heat to increase the temperature by 1 degree Celsius, right? So the energy that takes any amount of a compound to increase 1 degree Celsius is the heat capacity. So that's why we have the M, the mass, times the specific heat is heat capacity, okay? So we use heat capacity and specific heat. Why do we use it like that? So the heat capacity, the specific heat capacity, the first one, the specific heat capacity is specific for any elements, okay? We can say exact numbers for each matter. Like if we can say aluminum, for example, have this number, and there's a chart that you can see in the next slide. Aluminum specific heat is this number, and it's a fixed number because it's specific to that element, okay? It's for just 1 gram of that element for 1 degree Celsius, okay? And that's a measurable number, and that's a constant number. Heat capacity is for items that have a certain mass. You're going to learn about calorimeters, and you know the calorimeter consists of different things with different masses, and if they give you the specific heat of each component, you have to find the mass of each component, multiply the mass by the specific heat, and then you can find the heat capacity of the whole thing. Okay, instead they give you the heat capacity of the whole thing. Okay, so that already taken care of the mass and the specific heat capacity. Okay, so you don't need to worry about the mass. So heat capacity is the mass times the specific heat of that element. And you know it needs require more energy to increase the temperature, right? So what if the change in the temperature is not 1 degree? So you have a change in temperature in an item in your system that which is like 5 degrees Celsius. That definitely needs more heat to raise that temperature, right? So that sum up the formula to find the heat to find the heat for your system. So if you have the specific heat and if you have the mass, if you multiply the mass by the specific heat, gives you the heat to increase it for 1 degree Celsius. But if it's not 1 degree Celsius, it's more than that, you have to apply that too. So if it's like 5 degrees Celsius, if it's going from 20 to 25, so you have 5 degrees Celsius. So you have to multiply by the difference in temperature. So that sum up our formula for calculating heat absorbed or released by an object. Okay. So you can see that there is a delta T in the formula, and the delta, you know, it's final minus initial. Final temperature minus initial temperature. And if the change in the temperature, if it going to the higher temperature, so T final is higher than T initial, therefore delta T is positive. If it's losing energy, so the temperature is going down, so delta T is a negative. So that already take care of the sign of the Q. So to find the heat of the system, you can use this formula. I write it again here. So Q equal MC delta T. It's also famous by the name QMCAT. So if you see here, it's C delta could be CAT, so MCAT. So it's famous to say QMCAT. Okay. So you can, M is the mass, C is the specific heat, and delta T is the change in temperature, right? So Q MCAT. That's how you can find the heat of the system. So delta T is in degrees Celsius, is the same as degrees in Kelvin, because you know the scaling in Kelvin and Celsius is the same. There is only the difference of 273. So 0 degrees Celsius is 273.15 degrees Kelvin, but the scaling is the same. But the scaling in Fahrenheit is different, right? So the delta T in Celsius and Kelvin are equal, but it is not equal to the delta T in Fahrenheit. So if you're given the temperature in Fahrenheit in a question, you have to convert that to Celsius and then find a delta T. And these are specific heat. I told you have it in the table. So the specific heat capacity for each element is specific to that element. That's why it's called a specific heat capacity. Okay, so you can find that's a constant number, and you can find it in the table. Usually in a question, the C is given. When we ask you to find the Q, the specific heat of that compound is already given in the question. You don't need to memorize these numbers. Okay, so now let's have some practice. So calculate the amount of heat liberated in kilojoule, pay attention to that, from 366 gram of mercury when it cools from 77 degrees Celsius to 12 degrees Celsius. You have the specific heat of mercury, and the unit of that is joule per gram per degree Celsius. Okay, so you know that formula, Q equal mcat, mc delta T. So the mass, we want to find the Q, right? The mass is in gram, so the unit, so we have to pay attention to that. The unit for specific heat is joule, gram, and degrees Celsius, okay? So we can use the mass in gram, so that's fine. The mass is 366 gram times C. We have the C, we have the specific heat, which is 0.139 joule per gram per degree Celsius. And the delta T is T final minus T initial. It's cooling down from 77 degrees Celsius to 12. So T final is 12 degrees Celsius minus T initial 77.0 degrees Celsius. Okay, so gram with gram and C degrees Celsius minus degrees Celsius end up with degrees Celsius with a number, and you can cancel these two together. We end up with joule. Okay, we want the answer in kilojoules, so let's first find the answer in joule and then we convert that into kilojoule. Okay, so the change in the temperature is 65 degrees Celsius, and if you put these numbers in your calculator, you will get Q as 3,306 joule, and we want it in kilojoule, so we have to convert it. We don't want joule, we want kilojoule, and 1 kilojoule is 10 to the 3 joules, and that makes it 3.31 kilojoule. And the sign is, I missed that. You have to be careful with this. I always usually do it in the end, and then I think about, whoa, was it negative or positive? So you have to be careful. So the delta is 12 minus 75, so that makes it a negative delta T. Therefore, the Q is negative 3000, and when you convert it is negative 3.31. Okay, so the answer is B. Okay. Okay, so heat as a form of energy, as a thermal energy, we said we have a transfer of the energy, right? And thermal energy, as a type of energy, we have a transfer of thermal energy. So when we have two objects in a place next to each other that they have different temperature, they have different thermal energy, they start to transfer the heat until both of them have the same same temperature, okay, or same energy, okay. But since the total amount of energy of the universe is constant, and we can apply that to the thermal energy as well, so the Q of the system is equal to the negative sign of Q of the surrounding. Okay, so if you think about, if you look at the picture on the right, we have a cube of ice, right? So it has low temperature, and we have it in water. So if we consider the ice as a system, or, well, it's not the ice, I subscript it as metal. If it's a metal with a different temperature, so we put it in the water, they start to transfer the thermal energy until they reach the same temperature, okay. But the amount of Q that the metal is gaining to become warmer if it's cold is equal to the same amount of energy which is taken from water with a different sign. So water is losing energy, metal is gaining energy, okay. So the amount is equal, the sign is different. Okay, so now think about this example. What is the specific heat capacity of an unknown metal We said it's unknown because if it's a known metal, the specific heat capacity is always a constant. You can look up in a chart and find it. Okay, so an unknown metal, if a 25.5 gram of that metal at 115 degrees Celsius is submerged into water, how much water? 101.5 gram of water at 25 degrees Celsius. The final temperature of the water is 27.75. So we say the final temperature. What state is the final state? We say it when they do the heat transfer until both of them have the same amount of thermal energy or same amount of temperature, right? So the question says the final temperature of the water. What is the final temperature of the metal? Yes, they should be in the same temperature, right? So the final temperature of the metal also should be 27.45 degrees Celsius. Okay, assume that the metal, and I don't know why it's aluminum, it should be water, and don't take it as it's aluminum. So you go and look up the number for aluminum, because they usually make up these numbers to just work, and the number might not match with the specific heat of the aluminum. Okay, so it's just a typo. So assume the metal and the water are isolated from everything, and we always add these things, or sometimes we say assume that the heat loss to the surrounding is zero, something like that. So because if we have the heat loss from the beaker, from the container to the room, then it messes up the calculation. So we take this assumption so that we can say that the amount of the Q of the metal is exactly equal with a different sign of the Q that water gained or lost. Okay, so the Q of the water is exactly equal to the Q of the metal, not metal. I'm sorry. Okay, metal. Okay, Q of the metal is exactly equal to the Q of the water. Okay, so what do we have? We have, as we are reading the question, we want the specific heat of the metal, right? We have the mass of the metal, so on the metal side we have the mass, and what is that? 25.5 gram. Okay, and we have the temperature, so is it final temperature or initial temperature? It's the initial temperature of the metal, and this is 515 degrees Celsius. Is submerged into water. So what do we know about the water? The water mass, we know the water mass is 101.5 gram of water, and at this temperature, again, this is the final temperature or initial temperature. It's the initial temperature of water, degrees Celsius. The final temperature of the water is 27. So I know that final temperature, so TF of the water is 27.45 degrees Celsius. What is the final temperature of the metal? Yes, it's the same temperature, right? Because we said they transfer heat until they have the same temperature. So the final temperature for metal should be the same as water, 27.45 degrees Celsius. Okay, so for Q of the metal, you know that the Q is MCAT, right? So I don't write the Q. So instead of Q, I write M of metal. I just subscript it as M of metal equals C of the metal, the delta T of the metal, equal the negative sign of M of water, I subscripted with W, times C of the water and delta T of the water, right? I can write that. So we have the mass of the metal. We are trying to find the specific heat capacity of metal, so we don't know that. We are trying to solve for that. The delta T of the metal, do we know that? Yes, we have T final and T initial. We can find that. So this is known, this is known. The mass of water is known. The delta T of water is known. The C of the water, I told you, usually give you the specific heat. This is not given in this information in this question, but you can find it in the table. but on the exam, I mean, this is not information I want you to memorize. Okay, so this is something I will give you. It's not in this information, but you can find it in the table. But I mean, don't worry about this as memorization. Okay, so we can find that as well. So we can solve it for Cm. So to solve it for Cm as a specific heat capacity of metal, so we have that if you divide all of these by m of the metal and delta T of the metal, m of the metal and delta T of the metal, then you can solve it for the, I write it here, for the heat, specific heat of the metal. Okay, okay, so we have a negative sign. The mass of water is 101.5 gram times the C of the water. You can find it from the table, but I know it's 4.18 joule per gram per degree Celsius, and multiply the final minus initial. So the final minus initial for water is 27.45 minus, I write on the top, 25 degrees Celsius. Okay, and on the denominator I have the mass of metal, which is 25.5 gram times the delta T of the metal, the T final, which is 27.45 degrees Celsius, minus the initial temperature, which is 115 degrees Celsius. Okay, I just want to double check everything's right. Yes. Okay, so the gram with gram and degrees Celsius with a degree Celsius of a delta here, and so we end up with joule on top and gram with degrees Celsius on the bottom, and that's a unit for the C. Okay, so if you put all of these numbers in the calculator, what do you get? You get 0.466, and the unit we have joule on top and gram and degrees Celsius, so it's joule per gram per degree Celsius. So that's the specific heat capacity of the metal. So we talked about the first law of thermodynamics in the previous video, and we said there are two ways for the system to lose or gain energy, which is heat and work. In this video, we talked about the calculation, how we can calculate the heat lost or gained by the system, which is QMCAT. So you need the mass, you need the specific heat, and you need a delta T, the change in temperature, to find the heat. In the next video, we are going to talk about the calculation to find the work of the system.